Okay.
Good morning, ladies and gentlemen. Thank you for attending our keynote talk in this morning. This is the third day of conference AUA-SEGT 2022. Okay. So today we are glad to have Professor Michael K.H. Leung from Hong Kong to deliver his plenary talk titled Ammonia, a green fuel for renewable energy storage and utilization. And let me start with the introduction for Professor Michael Leung. He started his academic career as a lecturer in the Department of Manufacturing, Engineering and Engineering Management at the City University of Hong Kong in year 2000. In 2002, he joined the Department of Mechanical Engineering at the University of Hong Kong as a research assistant professor. And in 2006, he became an assistant professor. In 2010, he joined the City University of Hong Kong again as an associate professor in the School of Energy and Environment. He also served as associate dean, undergraduate study in SEE since year 2012. In 2015, he became a professor. Professor Leung's main research interests are solar photocatalysts, fuel cell electrochemistry, hydrogen production, carbon management, carbon capture and storage. He is listed as a highly cited scholar in energy science and technology. Since 2002, he has totally received the research funding in the amount of Hong Kong dollar 18 million as a principal investigator from ITF, RGC, ECF, and WWGF. He also received some industrial sponsorship. He is the editor-in-chief of Hong Kong Institute of Engineer Transaction, HKIE Transaction, and editorial board member of Applied Energy. He has published more than 120 journal papers and 15 book or book chapter and granted 6 patents. Professor Leung is also a past chairman of the Energy Institute Hong Kong branch, a member of Hong Kong Advisory Committee, HKSAR, Energy Discipline Representative in HKIE Education and Examination Committee. He is also a chartered engineer and a registered professional engineer. Please welcome Professor Michael K.H. Leung for his keynote talk. Thank you. Professor Michael.
Okay.
Michael Leung.
Okay.
The floor is yours.
Thank
Please.
you. Thank you, Professor Zhang, for the nice introduction. Okay. So and I would like to also thank all the organizers for organizing the AUA-SEGT 2022 conference. Okay, so that we have a nice platform to share knowledge. Okay, so today I would like to share with you about ammonia fuel, how we can use it, okay, as an effective energy carrier to facilitate the development of renewable energy. And here is the outline of my today's presentation. I will talk about the properties of ammonia, why these properties make ammonia an effective energy carrier. And then I will also talk about different technologies. We have done research recently, and in our ongoing research, they include renewable ammonia production technologies and also ammonia fat fuel cell. And in my presentation, I will also address the future development of this technology. Yes. Okay. Just a moment. Can you see the screen? Is it moving? This is the whole. I already done the full screen. But I have already done the full screen on my laptop. I share the screen. Okay. How do I share the screen? Let me see. Okay, entire screen. I share entire screen. Is it okay? Is it moving? Okay, thank you. Thank you. Okay, so okay, so let's move on. Okay. Okay, we are familiar with hydrogen. Some of the speakers, keynote speakers, have also talked about hydrogen energy in the past couple of days. So in a hydrogen economy, okay, here I show our general systems, okay, that will include renewable hydrogen production. Okay, we can use solar energy and wind power and to produce hydrogen. Okay, and then hydrogen can be distributed to the city, okay, for utilization. However, since renewable energy is intermittent, we need to have a storage, okay, to store the hydrogen produced when renewable energy is available, and then later when renewable energy is not available, we can use the stored hydrogen to supply power. Okay, so it's not only storage. Okay, we also need to transport. Okay, because an effective way to produce renewable hydrogen is to use a central, large scale renewable energy hydrogen production plant. So we produce a lot of hydrogen, and then the hydrogen can be transported to different part of the world. Okay. Okay, so and then of course for the utilizations, okay, one of the most effective way to use hydrogen is to use fuel cell to convert it into electricity directly. Okay? So we have stationary fuel cell. We also have a fuel cell cars. Okay, okay, so here is hydrogen economy, and then we have researchers. Scientists have already developed, okay, all kinds of technologies to facilitate hydrogen economy. Okay, still, okay, but during the implementation, we still have issues about the storage and transport. Okay, because the storage may involve a high pressure compression. Okay, if we want to store hydrogen as a vapor, or we liquefy hydrogen, but by doing this, we need to cool it to very low temperature. Okay, and also, okay, the storage may cause risk, okay, hazards. Okay, so there are issues about hydrogen storage and transport. Okay. Okay, so these are the general properties of hydrogen. Basically, it's showing that why hydrogen. Okay, number one, energy content is very high. Okay, and number two is the main point is it is a vapor. Okay, the boiling point is very low, 20 degree Kelvin. Um, and the density is also very low. Okay, so as I said, okay, either we use high pressure compression or we have to cool it to very low temperature for liquefaction. Okay. So these are the table that summarize the two storage methods. Okay, and what are the limitations? Okay, maybe we can look at some numbers. First of all, either method will consume energy. The energy efficiency of high pressure compression storage method is 93%. Liquefaction, the efficiency is lower because it takes a lot of energy to cool hydrogen to liquid. And then the other limitations is the low gravimetric density. We can store, need roughly 1% of hydrogen. And then the remaining weight will be the high pressure vessel. And then the last one is safety is a real concern. Okay, when we store and transport hydrogen this way. Okay, then what is there any alternative? Okay, then nitrogen has been ammonia has been identified as an alternative. Ammonia, okay, NH3. First of all, it contains a lot of hydrogen in the molecules. Okay, and then here I also list other advantages. Okay, one main advantage is about its properties. It can be easily liquefied. Okay, and then it can be transported as a liquid at low pressure, near close to the ambient condition. Okay, and down to the list, it also has a low flammability risk. Okay, so come back to this hydrogen economy. So if we want to adopt ammonia fuel, okay, these are the changes needed. Okay, we want to develop an ammonia economy. So number one, to start with, we need to produce ammonia in a renewable manner. Okay? And regarding the storage, we no longer need high pressure vessels. Okay? So conventional, okay, fuel containers will work effectively. Okay, so ammonia, of course, once we have ammonia, it can be easily converted into hydrogen by heating, okay, by a pyrolysis process. Okay, however, a more effective way or better efficient way to use ammonia fuel is ammonia fuel cell. Okay, can we develop ammonia fuel cell so that the fuel cell will work with ammonia directly? Okay, so we can look into some of the works we have done. Okay, first is renewable ammonia production. Okay, when we work with hydrogen, okay, we will apply electrochemical process. Okay, we use electrolyzers to produce hydrogen. Okay, by consuming electricity. Okay, then water can turn to hydrogen. Okay. The same system. Okay, electrochemical process. Okay, electrolyzers. Here I'm showing that it will also work. Okay, to convert nitrogen into ammonia. Okay, the source of nitrogen is from the air. Okay, we have 79% nitrogen from the air, and the hydrogen can come from water. Okay, so here shows the electrolyzer for the electrochemical nitrogen reduction reactions. Okay, the abbreviation is NRR. Okay, so we need to develop effective electrochemical catalyst for this NRR reaction. Okay. So this has been the focus of my recent research. Okay, so some of the background information is about the properties of different metals candidates for the electrocatalyst. And this is a popular, well-known volcano plot for the nitrogen reduction reaction. And here, where the material close to the peak represents that they are effective candidate electrocatalyst. Okay, so molybdenum, okay, has been identified as one of the most effective catalysts. Okay. So in our recent research, okay, we adopt this general methodology. We produce the materials. Of course, we start with the design and produce the materials, and then we study their properties, okay, by doing different kinds of material characterizations. They are nanomaterials, so these are the nanomaterial characterizations experiments. Okay. And then we will test their electrochemical properties, and at the end is directly what is the performance for nitrogen reduction reaction. Here I can show some of the material we studied in the past. Okay. The first material we worked with was molybdenum carbide. As I mentioned, molybdenum has been identified as an effective electrocatalyst. Okay. So we produce the materials, we study their nanomaterial properties. Okay. And here I would draw your attention to the chart here. This is how we applied these materials in our reactors to produce ammonia. Okay, so we measure the ammonia yield. Okay, we also need to measure the efficiency of the ammonia production process. Okay, so the Faradic efficiency will report this energy efficiency. So we can for all the material we developed, we also study their stabilities. Okay, we measure we repeat the experiment for many cycles and to measure their repeatability. Okay. So here is the summary of the materials we developed. Okay, when we compare our work among other materials developed by others and published in the literature, okay, the material we developed show in the last row. Okay, it shows that we can obtain high yield of ammonia, and also the efficiency, okay, is on the high side. Okay, so this is our earlier work, and then later we continue to develop more electrocatalysts. Okay, the next one is the molybdenum and cobalt bimetallic nanoparticle electrocatalyst. Okay. Separately, molybdenum and cobalt are good candidates. Okay. And then we also identified that when we produce the composite materials, okay, there are synergistic effects. Okay. So that we design these materials. Again, we produce the material and perform different tests. Okay. So here is a performance. Okay, we managed to increase the ammonia yield, and also we increase the efficiency of the materials. Okay? And further development is related to the dimensions of the materials. So here, the trend of the effectiveness of the catalyst versus the dimension is an inversely proportional relationship. Okay, when the catalysts are at a small size, okay, they tend to work better. Okay, then we continue to study material that has a smaller dimension. We study nanorod, and then ultimately, okay, we look into this. Really the smallest dimension is on the atomic scale. Okay, it's a single atom catalyst. And then this is our ongoing studies. Okay, we study when we have designed the material with molybdenum and cobalt. Okay, on the atomic level. Okay, and apply this material for electrochemical nitrogen reduction reactions. Okay. So let me show that. Okay. Okay. So this is our recent findings. Okay. Then the ammonia U is at a high rate, and more importantly is the faradic efficiency. Okay, we managed to again obtain it to around 26%. This is close to the highest faradic efficiency ever reported in the literature. Okay, so besides experimental work, we also verify our study by a modeling study. We conducted the density functional theory analysis, okay? And the findings, modeling results are consistent with our experimental findings. Okay, besides electrochemical process, okay, another promising ammonia production method is solar photocatalysis. So for the photocatalyst, okay, these photocatalysts are designed to be activated by sunlight. Okay, so that the source of energy is renewable and is free of charge. And we developed the iron-based photocatalyst, okay, that can perform nitrogen reductions. Okay? And this photocatalyst, after it is activated, okay, it will convert nitrogen and water into ammonia. Okay, so these are the material characterization we have done. Okay, for the material we developed, and we also measure. Okay, here is the production rate of here the last one is the U of ammonia. Okay, so this is another promising technology. Okay, then come to the last one is about utilization of ammonia. Number one, ammonia can be converted into hydrogen. Okay. And then we use a conventional hydrogen fuel cell, okay, to produce electricity. This is one way, and we also identified that if we can design our fuel cell so that can convert ammonia fuel directly, okay, that will increase the efficiency of the energy conversion. Okay, so solid oxide fuel cell is the technology that we can apply here. There are two types of, well, first of all, this is a conventional type of a solid oxide fuel cell. The electrolyte is designed to transport oxygen ion. Okay? And then in our study, we developed a better fuel cell. Okay, this is also a solid oxide fuel cell framework. However, we find that if we design the fuel cell for a proton conducting electrolyte, okay, then this is a more efficient energy conversion process. Okay, so the proton conducting solid oxide fuel cell is a better technology for the use of ammonia fuel. Okay, so we study the power output of the system. Okay, so here is the general concluding remark. Okay, ammonia fuel, okay, is an effective fuel that can facilitate the development of renewable energy. It has many advantages, okay, over hydrogen. Okay, it is, number one, it is safer to use, and it is easier to store and carry. Okay, and at the end, I would like to acknowledge my research team and the funding sources that support my research, the research I have just presented in this presentation. Thank you.
Thank you, Professor Michael Leung. Thank you for your interesting talk. So now I would like to open the Q&A session to the floor. So all participants, if you have any question, please move to the stage. You can take the staircase, the two staircase in front of the stage or podium, then move up to the light blue color box with the speaker icon. Then you can talk to everyone, including the speaker in this room. Please. Or you can choose to type your question in the chat box. Then we can forward the question to the speaker later. And for your information, all participants, this afternoon, our Kuala Lumpur time, 2:30 p.m. is our award announcement and closing ceremony. We have the Best Presenter Award and Best Poster Award. So all participants, you are welcome to attend the award announcement and closing ceremony from 2:30 p.m. to 3 p.m. So if there's no more question from the floor, once again, we thank Professor Michael Leung for his resourceful talk. And the participant, you can move to room A or room B, since there are two parallel sessions. Now, it's starting in 1 or 2 minutes. So see you again.
Okay, thank you.
Okay, thanks, Professor Leung. Okay, we meet again somewhere
Maybe
soon after pandemic.
I'll see you around.
Yeah. Bye bye.
Online.
Bye bye. Yeah.
Bye bye.
Yeah.